Hello, class. So today our agenda is to discuss the next topic, which is on the internal combustion engines. Okay, so in gas power cycles, the working fluid remains as a gas throughout the entire cycle. And examples of gas power cycles are the spark ignition engines or the gasoline engines and the diesel engines and also the conventional gas turbines. Remember in previous examples on the Rankine cycle, our working fluid, which is water, is actually transformed from a subcooled liquid to a saturated vapor to superheated steam and then to saturated fluid again and so on and so forth in a cycle. But in gas power cycles, the working fluid remains as a gas, okay, throughout the cycle. Therefore, during the combustion of air and fuel, so usually, diba in our Rankine cycle, the in the boiler, that's where combustion happens, and the combustion would heat the working fluid, which is water. But in internal combustion engines, the reaction of the air and fuel form the combustion gases. Okay, so remember your ChE 32. After combustion, the combustion gases will form, and this will serve as our working fluid. That's why they are called internal combustion fluid, right? Because the combustion products serve as the working fluid. On the other hand, in our steam power plant, in the Rankine cycle, these power plants may be called external combustion engines because, as I've mentioned, heat is transferred from the products of combustion, okay, to the working fluid, which is water. So they're not in direct contact with each other. Okay, so what are examples of internal combustion engines? We have the two-stroke cycle and the Otto cycle, or the gasoline engines. For the two-stroke cycle, it the cycle is one power stroke for every two strokes. So up and down, the movement is up and down of the piston. It's less efficient, and we will commonly see this in motorcycles, chainsaws, and lawnmowers. So, maliit lang yung engine. On the other hand, for autocycle, it's based on a four-stroke cycle. Okay, so yung una, two-stroke, this time four-stroke cycle. There's one power stroke for every four strokes. And it uses a spark plug. I'm not sure if you're a car enthusiast, but I'm sure that you have heard about that part in a car, in a gasoline car, that it has a spark plug. Gasoline is used as fuel, and we can commonly see this in cars, large boats, large motorcycles, and light aircrafts. Right. So this is um, an ideal auto cycle. So by the way, when we're talking about an ideal auto cycle, an ideal diesel engine, later we will discuss that. We call that air standard power cycle. So this refers to the ideal counterpart or the ideal cycle. The cycle consists of four internally reversible process. Like first is, so let's look at the TS diagram and also this uh, figure right here and the PV diagram at the same time. So steps 1 to 2, okay, is the isentropic compression. So isentropic, vertical line sa TS diagram. Sa PV diagram, ito yun, isentropic 1 to 2, saan siya dito? Okay, so the first step is isentropic compression. So air is the working fluid, and we assume that it's an ideal gas. Okay. Step 2 to 3 is constant volume heat addition. So, ito yon sa TS diagram, sa PV diagram, this is constant volume. So, since V yun nasa x-axis, this is a vertical line. And in the diagram, this is the step, constant volume heat addition. So, di nagbago yung volume. The piston remains at the same position. And we added the heat. Next step, 3 to 4. Isentropic expansion. So, ito yun, isentropic expansion. 3 to 4. So, I forgot to mention, so kanina do sa 1 to 2, compression siya, di ba? Kasi 1 to 2, lumiit yung volume, tumaas yung pressure. Okay? So, sa 3 to 4, expansion, lumaki yung volume, bumaba yung pressure, and isentropic siya. So, ito yung nangyayari. The piston moves down. Okay, the piston moves down, lumaki yung volume, bumaba yung pressure. Last step is 4 to 1, constant volume heat rejection. Okay, so ito naman yon. Heat is rejected at constant volume. So the piston position remains the same and the heat is rejected. And this happens in a cycle. This is an ideal Otto cycle. Okay. So when we look at the thermal efficiency, oh, by the way, this slide is from Ma'am Rowie's slide. Basahin nyo rin yung handout or slides ni Ma'am Rowie. May mga additional information there uh, that cannot be seen in the current slide. Okay? So, credits to Ma'am Rowie for the slides. Thermal efficiency of an air standard Otto cycle. Again, air standard Otto cycle, we're referring to the ideal Otto cycle. So remember our equation of the thermal efficiency. It's the work net over the QH or the Q in heat absorbed or heat that is added to the system. Okay. So we can adapt that in our auto thermal efficiency equation. Remember, so yung QH natin or yung heat addition, saan ba nangyayari? Saan step? Sa D to A, so steps D to A in the diagram is the constant volume heat addition. So we replace that the denominator with Q sub dA, and our work net is actually Q dA plus QBC. But remember that yung QBC negative yung value niyan. Okay? So but we just use positive, pero this itself would have a negative value kasi it's the heat that is rejected from the system or going out the system. Okay. So, yung addition ng dalawa yan would compose the work net. Now, for the process na D2A, constant volume heat addition, we can use sa isochoric equation. Remember, for a closed system and constant volume or isochoric, we use this equation. Q is equal to CV delta T, wherein CV is the constant volume heat capacity. So, and also for B2C, which is another constant volume process, constant volume heat rejection, yung Q natin dyan is just equal to CV delta T. Okay, so given our equations, we substitute yung QDA and QBC into the efficiency equation and rearrange, okay, cancel out the CV that um, is both on the numerator and the denominator. The Otto cycle efficiency equation is simplified to this equation, which is now in terms of the temperatures. So if we know the temperatures at each point in the cycle, then we can compute the Otto efficiency. Again, this is assuming an ideal cycle and assuming that our heat capacity is constant and not a function of temperature. Okay, so those are the important assumptions when we use this equation. Again, anong significance nito? It's we can use this as a standard or basis of what an ideal efficiency what's the ideal efficiency of that auto engine working at these temperatures. Okay, but again, this is for an ideal cycle. So what if we want to express the auto efficiency in terms of the compression ratio? But first, what is the definition of the compression ratio? So compression ratio is just the ratio of the two volumes. Okay, itong high pressure and low pressure volume. So if we take the volume at point C, VC, which is the high pressure, okay, divided by the volume at point D, VC over VD, that's the compression ratio. And it's greater than 1 because VC is higher. So nasa numerator yung higher volume. Okay, so what if we want to express this in terms of the compression ratio? Let's derive the equation for that. So since our assumption is the air is an ideal gas, we can use the ideal gas equation. Okay. We substitute yung expressions ng T into the equation. So substitute mo yan, substitute mo yung TC, etc. So and so forth. Simplify the equation. Since this is our compression, we define this term VC over VD as our compression ratio. Substitute lang yung R. Now, itong term, let's focus on this term, itong mga pressure na term na to. Remember that may two adiabatic reversible steps. And for a closed system that's adiabatic, this holds true. PV raised to gamma is constant, where gamma is the ratio of the specific heat at constant pressure and constant volume. So remember that's from ChE 142. Okay? So adiabatic closed system, adiabatic and reversible closed system, so PV raised to gamma is constant. So therefore, PA times VA raised to gamma is constant. And because VD is equal to VA, okay, I replace yung VA dito with VD. The same goes for this term. And then, okay, so we can also express the pressure and volume in this equation. Now, combining these two equations right here and eliminating the volumes would give us this equation, which can be rearranged to this form. Okay, so if you want to derive it at home, much better. And then just rearranging again the equations, and since PC over PD is just equal to VD over VC raised to gamma using this equation, okay, and this term is 1 over R, which is the compression, reciprocal lang nitong compression ratio, so 1 over R. Therefore, this term right here is just 1 over R raised to gamma. Therefore, our efficiency is just 1 minus R times 1 over R quantity raised to gamma. Okay, so kanina we have a thermal efficiency in terms of temperature, and now we have a thermal efficiency in terms of the compression ratio. And what is the compression ratio? It's the ratio of the two volumes. Okay? Next. So what is the significance of the compression ratio? The higher the compression ratio, the higher the efficiency. Okay, as shown in the figure. But when a higher compression ratio is used, the temperature of the air-fuel mixture may rise above the auto-ignition temperature. So what is the auto-ignition temperature? It's the temperature wherein your fluid automatically ignites. So walang kailangan na spark, it will ignite on its own. And this happens during the compression process. So in actual auto cycle, meron kasing spark plug, 'di ba? So, but if the temperature is too high, hindi kailangan ng spark plug, nag-auto-ignite siya. And that phenomenon is called engine knocking or engine knock. I'm not sure if you have experienced this by probably in old cars, but engine knock in spark ignition engine cannot be tolerated because it hurts the performance and can cause engine damage. So it's not a good phenomenon, this engine knock. So we have to operate below the auto ignition engine. That's why there's a limit to the compression ratio. So again, we cannot freely um, increase the compression ratio because in spark ignition engine or gasoline engine or engines with spark plugs, it will cause engine knocking because of auto ignition. Okay? All right. So in actual auto cycle, so kanina we discussed the ideal auto cycle where all the steps are reversible, but in actual auto cycle, this is actually the diagram. Dito tayo mag-start. Kasi, sige, okay lang din naman dito. Again, the compression stroke, the piston moves up, volume is decreased. Okay, ito yun, compression stroke. This one, this curve right here. And then, may ignition. So, ito yung spark plug. Okay, may ignition. This is the power or expansion stroke. The piston moves down. Okay, piston moves down. Next is the exhaust stroke. Okay, exhaust stroke. Piston moves. Pistons move down. Okay, piston moves up. Sorry, piston moves up. Okay, and then exhaust valve opens. Okay, exhaust. Ito din pala. Okay. Ah, dito din pala yung ano, nag-expand siya. Okay, so ito yon. Ignition, then expansion. So ito yon. And then, exhaust valve opens. Okay, dito yon. Habang nagdi-decrease yung, so lumalabas yung exhaust gases. And then, back to, air fuel mixture will enter dito yon. Intake valve opens. Okay, and the piston moves down. So, kanina kasi sa ideal, merong mga constant volume steps. Okay, so dito, nan- walang ganon. Wala ding reversible. So, this is the actual auto cycle. So, let's watch a short video. Wait lang. How do I play this? Okay, so let's watch this short video. Credits to the owner. This is from YouTube.
How do car engines work? The internal combustion engine uses small controlled explosion inside the combustion chamber which pushes the piston down. The piston's reciprocating movement rotates the crankshaft to power the vehicle. All modern engines are 4-stroke: intake, compression, power and exhaust. During the intake stroke, piston moves down. At the same time, the intake valve opens and the air and fuel mixture rushes into the chamber. Next stage is compression, in which the piston moves back and the intake valve closes, compressing the air and fuel mixture. Then comes the power stroke, in which the compressed air and fuel mixture is ignited using a spark plug, which results in a controlled explosion pushing down the piston at force. The last stage is exhaust stroke, at which the exhaust valve opens and all the burned exhaust gas exits the chamber. The intake and the exhaust valves are controlled by camshafts. The camshaft is connected to the crankshaft. This whole process happens thousands of times in a minute. So again,
Okay, credits to the owner. So that's how an actual auto cycle or auto engine works. Let's proceed.
how do
Okay, next we move on to the diesel cycle. The ideal diesel cycle is also an air standard power cycle. So it's like the Otto cycle. It's based on a four-stroke cycle and employs compression heating ignition system. So in gasoline engines, remember we have a spark plug, but in diesel engines, it's replaced by the fuel injection, and only air is compressed during the compression process. Diesel engines are used in automobiles, heavy trucks, heavy equipment, and electric generating plant. This is an ideal diesel cycle. Um, Again, we have the PV diagram and TS diagram. The steps are first isentropic compression, just like in the auto cycle. So steps 2 to 3, this is where they are different. Okay, it's constant pressure heat addition. Remember, in auto engines, this is constant volume heat addition. Okay, but for diesel cycle, it's constant pressure. Next step, pareho lang din sila 3 to 4 isentropic expansion and then constant volume. Okay? So sa PV diagram, yung step 2 to 3 constant pressure. Sa auto engine, yung steps 2 to 3, okay, vertical line to constant volume. Okay, nakuha ba yung difference ng dalawa? Okay, so this slide is from Ma'am Rowie's handout. Uh, Basically, it just presents the efficiency of a diesel engine or an ideal diesel cycle. Okay, hindi na pinakita yung derivation. Uh, Now we have another compression ratio. So, by the way, wala dapat tong E, dapat R lang to. Okay. Compression ratio is VC over VD. Okay, the highest volume divided by the lowest volume. And now we have another term that we need to define, the expansion ratio. Expansion ratio naman is VB over VA. Okay, ito naman yun, VB over VA. And it's R sub E. So, compression ratio R lang to. Okay, tanggalin yung E. Expansion ratio is R sub E. And the efficiency of the ideal diesel cycle or the air standard diesel cycle is given by this equation. Again, assuming CP over CV is equal to gamma and um, PV raised to gamma is constant. Okay? Or the specific heats are not a function of the temperature. Before solving sample problems, let's finish the discussion first. So, ibang video na lang yung sample problems. Okay, now we move on to Brayton cycle. Okay, it's previously called gas turbine engine, and it has three components: a gas compressor, a burner, and an expansion turbine. And the cycle involves two constant pressure and two isentropic processes using a single-phase gaseous working fluid. Okay, so we're still discussing the single-phase gaseous working fluid, whereas yung previous natin, yung steam power plants, changes phase. Okay. So the air standard Brayton cycle is the ideal Brayton cycle. Again, yung term na air standard, so we're referring to the ideal cycle. Okay. And there are two types of Brayton cycles, the open cycle and the closed cycle. First, let's discuss the Brayton open cycle. So here, fresh air at ambient condition is drawn to the compressor where its temperature and pressure are raised. Okay, and then the high pressure proceeds into the combustion chamber. Okay, so may fuel, combustion chamber, and the fuel is burned at constant pressure. So the resulting high temperature gases enter the turbine where they expand to atmospheric pressure, okay, while producing a network or producing power. And the exhaust gases leave the turbine. They are not recirculated. Okay. And as you can see here, some part of the work of the turbine drives the compressor. On the other hand, the Brayton closed cycle compression expansion process remains the same. Okay, so this is the same, but the combustion process is replaced by constant pressure heat addition from an external source. So kanina kasi yun mismo ah yung air na pumasok sa compressor, yun mismo yung hinaluan ng fuel. So for this one, combustion process is replaced by a constant pressure heat addition from an external source. So, external source, meron lang heat exchanger. Okay. Tapos, the exhaust process, so dito tayo, is replaced by a constant pressure heat rejection to ambient air. So, may heat exchanger din. Okay? So, may heat exchanger dito, tsaka dito. And the exhaust gases are recirculated. Again, part of the work produced by the turbine is used to drive the compressor. So if we want to calculate the efficiency of the Brayton closed cycle, so we can use this equation. Okay, so if we start with the efficiency equation where in 1 minus QC over QH, QC is the heat rejected from the heat exchanger, exhaust heat exchange after the exhaust, and QH the heat added in the um heat exchanger after compression. So remember, constant pressure process yung dalawang heat exchanger natin. So this equation holds true. Q is equal to Cp delta T, where Cp is the constant pressure specific heat. So we simply replace that with the Cp delta T for both steps. And then we cancel out the CP and rearrange and take out the T1 for the numerator and T2 for the denominator. And then since process 1 to 2, okay, are isentropic, okay, so refer to the TS diagram and PV diagram. So steps 1 to 2 and 3 to 4, okay, isentropic. P2, okay, P2 is equal to P3, P4 is equal to P1. Okay, this is for the Brayton closed cycle. This equation holds true. Okay, and replacing that, replacing the terms in our previous equation right here, we can then derive the equation for the efficiency of an ideal Brayton closed cycle. Okay, so this is the equation for the ideal Brayton closed cycle. Now, the term P2 over P1, by P2 over P1, P2 over P1 is called the pressure ratio. It's the pressure ratio. Okay. So, P2 over P1. Or P3 over P4 since isobaric to constant pressure yung 1 at 4 and 2 at 3. We also have another term called the backwork ratio. So what's the backwork ratio? Um, okay, it's the ratio of the compression work to the turbine work. So remember, in the Brayton closed cycle, part of the work of the turbine is used to drive the compressor. So we take the ratio of the work required by the compressor over the work produced by the turbine. Okay, so it's and replace expressing that in terms of the enthalpy, we have the backwork ratio. And the usual range of the backwork ratio is 40 to 80% for the Brayton closed cycle. Okay, we're done with the um, internal combustion engines and the Brayton cycle. Let's discuss jet engines. Okay. So in our previous discussion in steam power plants, gas turbine, auto, and diesel engines, remember that the power becomes available through a rotating shaft. Okay, so merong rotating shaft that drives the motor for the power generation. But in jet engines, expansion uh expansion is done through nozzles. Okay, through nozzles. And in jet engines, power is available as kinetic energy by the jet of exhaust leaving the nozzle. Okay. And jet engines are used to power aircrafts. Okay, so this is a schematic diagram of a turbojet power plant or the jet engine. So air enters the chamber, may diffuser dito, then may compressor tayo, and then combustion happens here. There's a turbine, and the unique part for jet engines is we have the nozzle, wherein the um, kinetic energy of the exhaust gas leaving the nozzle uh, is the source of the power. Okay, so this is the turbojet engine. On the other hand, rocket engines differ from jet engines because the oxidizing agent is carried with the engine. So dito kasi sa jet engine, the oxidizing agent is the air. So nandyan yung oxygen natin. So kailangan yan for the combustion. Okay. Pero for rocket engines, as you can imagine, if rocket engines are used like in outer space where there's vacuum, walang air, so rocket engines carry the oxidizing agent within the engine. So instead of depending on the surrounding air for combustion, the rocket is actually self-contained. Kasi nga, they have to operate in vacuum, such as in outer space. So this is a schematic diagram of a rocket engine. So may fuel, ito, instead of air, dala niya yung oxidizer niya, may combustion chamber. Like the jet engine, meron ding nozzle. And okay, yung kinetic energy ng exhaust gases, it drives the power of the rocket. Okay? Okay, everybody. So that ends the lecture. We will now move on to the sample problems in the next video.